Hi everyone, so we're now going to solve example 2, which is actually the same problem as example 1, but the solution requires that we use quadratic interpolation instead of linear interpolation. In quadratic interpolation, the main objective is to determine the curve that is obtained from using this equation. This equation is a quadratic equation, and in order to determine this equation, we need to determine these coefficients b0, b1, and b2. b0 is given by this, b1 is given by this, and b2 is given by this. We've already discussed how this was derived. These equations were derived from Newton's divided differences polynomials. And once we know these coefficients, we can just plug them in here and get an equation for the function that we're going to use as our solution to this problem. Before we move on with the video, I would like you to take note of the following. b0 equals 0, b1 equals this value, and b2 equals this value. Please write them down somewhere on a sheet of paper because we're going to refer to them as we watch this video. Also write these down, this value of f of 2 at x equals 2, and the error, which is 18.4%. Okay, now what I did here was I did not implement these expressions in MATLAB. Instead, I made a general implementation of the interpolation. And not just, when I mean general, it's not just for linear interpolation, for quadratic interpolation, but what I mean is I implemented in MATLAB an nth order polynomial interpolation, which means that I can type in these given values and type in also the order of the polynomial equation that I want to use, so that I don't have to type these equations over and over again every time I need to use them. Okay, and that's what I'm going to show you in this video. So just for a review, this is the general equation for the nth order polynomial. The idea is to determine these coefficients b0, b1, b2, b3 up to b sub n, where b0 is given by this, b1 is equal to f open bracket x1 x0 close bracket, b2 is equal to f open bracket x2 x1 x0, and so on and so forth. Now I also want you to write this down on a piece of paper because we're going to refer to them later when I show you how to implement these in MATLAB. Okay, now here is the MATLAB code. So if you recall, in example 1, I had all these values written out. Now, I want to show you an alternative of writing out these values. Instead of writing them out one by one, I have 6 variables here. The alternative is I can use just 2 variables, one variable for all x values and another variable for all y values. So what I did here is I wrote down xx as 1, 4, 6, so this is a row matrix. I can call this value, this is the first element in the matrix, so this is the index of this element is 1. This is the second element of the matrix, so the index of this number is 2. So what I mean is, if I have xx, okay, as the variable, I have this. I know that it's a row matrix because if I type in the size of x, that I have 1 row versus 3 columns. Also, I can call each element of the matrix like so. So that's x. So that's the first element of the matrix. That's the second element of the matrix, and that's the third element of the matrix. Okay. I did the same for f of x. So I wrote here fx equals 0, and then the second element and the third element, like so. This you've already seen in the previous video, as well as this. Now, also in the previous video, in example 1, I plotted the markings and made 4 commands for each of the markings. This time I shortened it by using the for loop. So I'm now plotting from 1 to length of xx. We know that the length of xx is 3, so type in length of xx. Oh, sorry. Length of xx is 3. So this runs from 1 to 3, which means that I'm plotting each of these elements, matrix elements here. So I'm plotting this, this, and this. So this is for I. This is the one that I plotted for I equals 1. This is the data point that I plotted for I equals 2, and the data point that I plotted for I equals 3. And that's what this for loop does. Okay, it's very convenient instead of typing each plot command one by one. Okay. Then the next is I plotted this true value of 2 versus log of 2, so which is this element here, okay, or this data point here. Okay, now we go to the main command or main code where I am able to determine the coefficients for nth order polynomial. Okay, let's begin with a linear or the first order polynomial. So this is where I type in the order. So n equals 1 is the first order polynomial or the linear polynomial. If you recall, this is the solution that we have. It's a linear solution and it matches perfectly with the solution that we obtained in example 1. If I type in 2 for the quadratic polynomial, then I have this equation, and it also matches perfectly with the solution in the example number 1. Of course, if I type in 3 here, it really doesn't do anything. And why is that? Because remember, for the first order polynomial, I need 2 data points. For the second order polynomial, I need 3 data points. And for the third order polynomial, I would need 4 data points. But in this example, we only have 3 data points. If I wanted to do a cubic interpolation, I need at least 4 data points. With the given values that we have, we won't be able to solve for the equation corresponding to the cubic interpolated curve. Okay, which is why I have this error message here: the order cannot be greater than or equal to the number of data points. That error message is something that I also generated, just in case n is greater than or equal to the length of xx, then it prints out this message in the command console. So let's continue with second order polynomial or quadratic polynomial. Now the main function is this, f of n, and this function generates the coefficients b0, b1, and b2 if n equals 2. Okay, now how do we do that? So let's go to the next slide. Let's begin with this. So we have the function f equals f of n, where f is your return variable. This f should contain your coefficients b0, b1, and b2. F of n is the name of the function. Okay, it should also be the same as the name of the file. These are your input variables x, y. X and y are your data points. So we have 3 data points for x and 3 data points, 3 elements for y. This is the order, which in this case now is solving for where n in this case now is 2. And this is the function, and this corresponds to the elements of the x component where we need to compute for the interpolated values. In other words, if I go back here, you can see that the fourth argument in the function fn is x, and x here is this one. So this is what I used to solve for the true value of logarithm of x, and this is also what I'm going to use to solve for the interpolated values of this quadratic line. The first step here is just tells you what the length of x here, so that I will be able to terminate the for loop, because I want the for loop to just run from an initial value to the maximum number of elements of x. And z here, this is just to initialize the variable z, which I'm going to use to compute for the coefficients of b naught, or in the case of what we've discussed earlier, these are your f square brackets. Okay, this is, so what this command does, so this command is code, or this code, this is colon comma 1. What this means is that I assign all elements of y to the first column. Okay, why first column? Because this second argument here corresponds to the first column, and this tells me that I want to put in these values at all row elements. Okay, so if, for example, I'm going to put y1 in z11, y2 in z21, and y3 in z31. And that's what this colon does. Okay, so next, I run j from the value 2. I already explained this earlier. And then I also run the index I from 1 to a minus 1, because if you recall, we don't need to compute for the maximum value of a. We just, for example, in this case, we have 3 elements or 3 data points, so we only need to compute up to the second data point, because otherwise it will generate, or the MATLAB will produce an error. So this is the equation that we need in order to determine the coefficients. Okay, and then remember that the coefficients are the first row elements of the variable z, so I assign the coefficients here, v. So let's now discuss how we are able to derive for the function or the basic equation that we need that MATLAB will understand. Okay, so I rewrote this table that you found in your notes. Okay, and what this does, or what this table contains, are the divided difference terms for each order. Okay, so first of all, let me identify your data points. Okay, we have these data points: x1, x2, x3, x4, f of x1, f of x2, f of x3, and f of x4. The indices begin from 1, 2, 3, 4. Okay, and the reason why the indices begin from 1 instead of 0, which you can find in your lecture notes. In the lecture notes, you have x1, x0, x1, x2, x3. Here we have x1, x2, x3, x4. And the reason for that, because MATLAB does not accept indices of 0, an index of 0. MATLAB begins, or the lowest index that MATLAB accepts is the index 1. Okay, which is why now I've written here an index I starting from 1 and going up in value. Okay, so these green circles here that correspond to your given values. Now these given values correspond to, in MATLAB, it will be written as x1, x2, x3, and x4 as you see. Okay, so x open close parenthesis 1, and so on and so forth. Okay, what about f of x1 and f of x2, or f of xi in general? How do you write that in MATLAB? Well, in this case, I wrote that like this: y of 1, 1 for f of x1, y of 2, 1 for f of x2, y of 3, 1 for f of x3, and y of 4, 1 for f of x4. So I used two indices, y. The first index is I, and the second index is j. The first index corresponds to the index corresponding to the placement of the number in the matrix or in the vector. The jth index, this one, corresponds to the order. It will be obvious later why we need a second index. In Newton's divided difference terms, we have for this term equal to this f of x2, which is what we have here, minus f of x1, which is what we have here, divided by x2 minus x1. So to get this, we need this. In the same way, to get this, we need these. To get this, we need these data points. Now, if you go to the second order, this one we obtain from this one and this one. Of course, we also need this and this, x3 minus x1. To get this, we need this one, and we need also this and that. Now, to get this one, we need this element here and this element here, and also x4 and x1, so we have this one and this one. So in essence, what we have here is something like this. So this is how you obtain your values for the second order. And for the third order, this is what you need to solve for the divided difference terms. Okay, and so on and so forth. Now, notice that we have these shaded regions here, or darker shaded regions here. And these, what you will find in these cells are how you implement these Newton divided differences in equation form. This is where the index j comes in. By using a second index, I'm able to go from the first order, which has an index of j equals 2, to the second order, which is an index of j equals 3, to the third order, which is an index of j equals 4, and so on and so forth. Okay, now in order to solve for y12, recall that we need this and that, and we also need x2 and x1. Okay, so y21 minus y11 divided by x21 minus x1. And to get y22, we need these two and these two. To get y32, we need these two and these two. In the same way, to get y13, I need this, and also these two. And to get y23, I need this, and these two. And to get the third order divided difference terms, I naturally need these two, and also x3 and x1, x4 and x1. Okay, and to get that, I need x5 here and x2 there, and also this and that. To go to the third order term, I need this and that. I also need x4 and x1. Now that we know the purpose of the first index and the second index, and we know how each of these equations were derived, the next step is to find a pattern. So what we need is a general term y equals yj is equal to something like I minus 1, j minus I minus 1, y of I minus 1, j minus 1 divided by xi minus yj, something like that. Okay, we want to have something like this, which we can plug in to MATLAB. Okay, so we need to study these carefully, each of these carefully, study the indices, so that we can derive a general expression for this. We know that the first index of y corresponds to I. We already know that expression, so we have y of I. What about the second index? The second index corresponds to the index j, which corresponds to the order. So for the first order, we have j equals 2. For the second order, we have j equals 3. For the third order, we have j equals 4. Okay, so if we want to solve for the j equals 2 terms, we need the j equals 1 terms here. If we want to solve for the j equals 3 terms, we need the j equals 2 terms here. As well as for the j equals 4 terms, we need j equals 3 there. So we can write this as y, then leave that to space, and then we know that this will be, if this is j, okay, this will be j minus 1 minus y, leave that as space, and then j minus 1 all over. Okay, now let's study the first index. So here we have an index of corresponding to I equals 1, 2, 3, 4. What about here? We have an index of 2, we have an index of 3, we have an index of 4, and we have an index of 5, which is initially what we suspect to be I plus 1, right? So let's see if this is correct. So this corresponds to 1, 2, 3, and this we have is 2, 3, 4. So again, that's correct, I plus 1. Here we have 1 and 2, and here we have 2 and 3. So that means that the first index in this term corresponds to I plus 1. And that's what we're going to write here. Okay, what about the index in the second term? Here we have 1, 2, 3, 4. And also we have 1, 2, 3 here. And also we have 1 and 2 here. So basically they're just the same as these indices here. So we can write I there. Okay, now let's go to the denominator. What will the denominator give us? Let's try to figure out what this index does first. We have 1, 2, 3, 4 here. Also have 1, 2, 3 here, and 1, 2. So that means that the index for the second term in the denominator corresponds to I as well. So we write down minus xi. Finally, what about this first term in the denominator? We have 2, 3, 4, 5. We have 3, 4, 5 here. We have 4, 5 here. So this actually starts from 2. And then we have 3 here. And then we have 4 here. Then as you go down here, we have an increasing index of 1 per term. Here it starts from 3 and it also increases by 1 per term. And here it starts from 4 and it also increases 1 per term. How do we relate that to I and j? So if you notice, if I add this and this, that's 3, right? And I subtract 1 from there, then I get 2, which is this index. Also, if I add these two, 2 plus 2, I have 4, and I subtract 1 from it, I get 3. 3 plus 2 minus 1 is 4. 4 plus 2 minus 1 is 5. Okay, so we have a working theory now. Maybe it's I plus j minus 1. Okay, let's see if this is correct. So here is 1 plus 3, that's 4 minus 1, it's equal to 3. We have 2 plus 3 minus 1 is equal to 4. 3 plus 3 minus 1 is equal to 5. Let's just verify for completeness here. So we have 1 plus 4 minus 1 is 4. And 2 plus 4 minus 1 is 5. So now we have our final index. So this will be x plus I, x of I plus j minus 1, okay, as we write there. So now this is the equation that we're going to use in MATLAB, because this is the equation that MATLAB should be able to understand. Okay, how do these correspond to the coefficients? Remember that the coefficients are given by these values. So the coefficients are given by y11, y12, so this is actually our b0, y13 is our b1, and this is b2. So we want to return only the y1 or the row terms or the row elements. So this is what we need to return or to use in solving for the coefficients. Okay, now that we have obtained, or now that we understand how the basic equation that we need, okay, in order to generate each of the elements or each of the coefficients, okay, so we write down that equation here. Okay, if you remember, our objective is to get this second order polynomial equation. We already obtained this in MATLAB, and we already know how to implement this in MATLAB. Now, how do we implement these products in MATLAB? So in the first term, we essentially don't have any expression for x here. In the second term, we have an expression x minus x naught. In the third term, we have two terms for x minus x naught and x minus x sub 1. So the question is, how do we implement this in MATLAB? I've rewritten this equation to this equation, where I simply change n to n plus 1, or all indices from n to n plus 1. So this becomes b1, this becomes b2, this is x1, this is n plus 1, x1, x2, x of n, okay, as you can see here. And the reason for the change is that, again, MATLAB does not accept an index corresponding to 0. MATLAB begins with the index 1. This term is the first term of the function f. This term is the second term of the function f. So this corresponds to I equals 1, this corresponds to I equals 2. I equals 3 corresponds to the third term in the function f. Our objective here is to determine this function f. In this code, I wrote that function f as the variable f. And I'm adding each term here, which is why for I equals 1 to n plus 1, yn plus 1, n plus 1 is here. So for y equals 1 to n plus 1, I'm adding this term to each iteration of f. Remember that vi is our b1, b2, b3, or the coefficients that we need to produce. What about these products? So if you notice that in the first term, we don't have any product of x. So what I did here was that I added another for loop. So that index for the for loop is j. And in the first iteration, or for I equals 1, I don't have any product here involving x. So what I did here is that for j equals 1 up to I minus 1, so since I equals 1 and I minus 1 is 0, so essentially the first iteration of this for loop will not give me any value of the product. And that's why I need this initialization here for the parameter or the variable product. What this once function does is that it creates a matrix with one row and the length of w columns. So we have I have here a row matrix with the length of W elements. All the elements in this matrix are simply have a value of 1. For I equals 1, the first iteration here doesn't do anything, so this doesn't do anything at all. So the product here is just ones. Okay, so it's going to be multiplied. So this term here, or B1, will be multiplied by a matrix once. So this will be the first term that will be added to F. Okay, so that's what we have here. By the way, this for I equals 1, this is actually 0. So what this does is that it generates a matrix, a row matrix with length or with a number of elements equal to the length of W, and all the elements are just zeros. So since all the elements here are zeros and I add here ones, and I multiply ones with Vi, so the first value of the variable f will just be ones times whatever b1 is. Okay, but we know b1 to be equal to 0. So the first element actually of f, or the first data set of f, will be just 0. Now when I equals 2, for the next iteration, I equals 2, okay, we have a reinitialization of the product. So this reinitializes the product to ones. Okay, now since I equals 2 here, then we have j equals 1 up to I minus 1. I equals 2, so 2 minus 1, so 1 to 1. So this iterates just once. So what we have here now is the product, which is equal to ones, times this, which is W, okay, which is the given set of X data, minus Xj, where X is your element or your data set. So this is X1. So this is X1 as it is written here. So X minus X1. And you understand now why I used W instead of X, because I already used X for the given variables. So this will give us just one factor of this term. So product will then be equal to W minus X1. And then it exits this for loop and then goes here. So product, or W minus X1, will be multiplied to B2, which is what we need essentially. And then it will be added to the initial value of F, where in this case we said that it's already 0. So this is 0 and this is the new product. So this is B2x minus x1. So this becomes B2x minus x1, whatever this data set contains. The next is I equals 3. So when I equals 3, then j runs from 1 to 2. So you have two products. The first product involves, for j equals 1, we have minus w minus x1. So j equals 1, we have w minus x1. And when j equals 2, we have w minus x2. So for j equals 1, product, or this product here is initially once, and it will be multiplied to w minus x1. So this becomes w minus x1. For j equals 2, this is already wx minus x1, and this becomes w minus x2. So this new value of the product is w minus x2. And then it terminates. So this product involves now w minus x1 times w minus x2. That's what we multiply with v2 in this case, since I equals 2. So v2 is actually b3. So b3 times w minus x1 times w minus x2. And that is added to the current value of f, which is b2 times x minus x1. So now f contains this term and this term. Okay, and you're going to do that for as long as I does not exceed n plus 1. So I hope you understand how this part of the code works. Okay, now that we've discussed how to implement that, we now have the function here. Okay, so we now have the function here. This function actually plots only this only this element here. Okay, but this plot command here plots this whole quadratic curve here. Okay, I can actually change this to a circle and decrease the number of data points here. For example, let's use 0.1 because what this, oh, yes, of course. Okay, now it should run. Okay, what this does is to just make the number of data points less fine, and now you see each individual data points or each individual interpolated data points between these original or given data points. Okay, so this is this graph actually is clearer instead of using a dashed line, and this again plots this curve. Okay, we can just simply make sure that we can solve for the error. So paste that there, and then divide everything by log of 2. Okay. And now we can solve for the error. Okay, and we see that the error is 18.4%, which is what we expected. F sub n, okay, is 0.5658, which is also what we expected if you take a look at your notes. Okay, so everything is in accordance with what we have, or what we already calculated by hand. Now, there's one more thing I'd like to show you in MATLAB. It will be very common for you to encounter lots of mistakes or errors when you run your code. And if you want to figure out how you went wrong, this is something that you can do. So one of the most common mistakes comes from evaluating parameters inside the function. Okay, I have this note inside the function f sub n, and you'll be able to see it when you download this function as well. It says here that the variables in these functions are unique to this function only. They're called local variables. This means that even if you use these variables in another script, this function script ignores all that and considers the variables here as local to this script only. What I mean is this. So I have x here, or x here, and n here, and so on and so forth. Okay, if I want to use any of the variables here, I have to insert that as a parameter in the function, like I did here, xx, fx, n, and x. So this actually is xx, this is actually fx, and this is n, and this is x in this script. But in this script, for where I generated the function, or where I made this function, these variables, okay, are only recognized here. In fact, when I run only this script, I won't be able to use any of, or I won't be able to see any of the values inside the script. Okay, so let me show you how this works, or what I'm trying to say. So this function has this variable a. Okay, so now let's try to run this main script. So I'm running this script, and I see, and take a look at my workspace. You see that it doesn't have the variable a at all. And the reason for that is because a is only used by this function. It's local only to this function, or to this script. So even if I type here a, it doesn't recognize that variable a. Okay, again, because it's local only to the function. What I can do here is, if I want to see what the value of a here, I can insert a breakpoint here. Okay, just click on this line here next to the number, and it inserts a breakpoint. A breakpoint is symbolized by this red circle. What this does is that if I run this code the code stops at the breakpoint, as you see here. So if I want to continue, I just press this step or press this continue button. Okay, so now I don't see the variable a yet, but if I add another breakpoint here and I press step here, I can see in my workspace that I already see the variable f. Okay, notice that you don't see as well the variables that I have in this main script. Okay, because again, these variables are local to this function. Okay, if I add another breakpoint there, I see z there. Okay, so this is what I mean by local variable. Okay, now what I would like to do at this point is to add a breakpoint here and then see what happens to z. So you see initially z equals, this command gives me a matrix with a elements and n plus 1 with a rows and n plus 1 columns. So a is 3 in this case and n is 2, so this will be a 3 by 3 matrix. You see here we have 1, 2, 3 rows and 1, 2, 3 columns. I know that they are columns because they are separated by this semicolon. Okay, so that's this part initializes the values of or the variable z. Now what this does is that this y is inserted into the first column. So if I press step, you see that the value of z changes. The first column, 0, 1.3863 and 1.798, which are the elements of the first column, okay, were changed. And these values were obtained from y, which in this case is actually our f of x. F of x are these. So 1.386294, which is what we have here, and 0, which is the first term, and the third term is 1.7918, which is what we have here. Okay, so that's what this line does. I inserted the values of y, or I introduced the values of y to the column elements of the column matrix for z. Okay, now if I press this, this is going to start to run and then end here. Okay, I'm going to add another breakpoint here so we will be able to see what the value of z is. So what this does is it generates the value of z at each row and at each column. Okay, so now I equals 1 corresponds to the zeroth order. I equals 2 corresponds to the first order, or sorry, j equals 2 corresponds to the first order, so that's what I'm going to compute here. I'm going to compute for the first order. The first order is actually b naught, which you already know. The j equals 2 term here is 0.4620981, and the j equals 3 term is negative 0.051873. I hope that you still have that in your notes. So let's continue with this. I press the step button. Okay, nothing changed here because it gives us 0 here. And now you see, well, you don't see anything yet. So let's see when the value of, okay, so j equals 2 here. So, okay, now you see for I equals 1 and j equals 2, the second or the first row and second column element was changed to 0.4621. This is your B1. Okay, and if I click on step here, okay, now let's go to what I equals 1 and j equals 3. So I should be able to solve for, or I equals 1 and j equals 2. So I should be able to see, okay, so okay, so now I have this, so 0, 0.4621, and negative 0.0519. So remember that all the elements of the first row of z corresponds to your coefficient. So this is b naught, b1, and b2. Or in matrix, this is or in MATLAB, this is B1, B2, and B3. So now we've already computed for the elements of the matrix. So this will just run until it's done with all the indices. And okay, now we have V equal to 0, 0.4621, and negative 0.0519. And the reason why that happens because I assigned the first row elements of Z to the variable V. Okay, and that's what we're going to use here. Okay, so I hope this video helps. Good luck.